All right. So welcome everybody to Hoon Academy Lesson 0. I'm super excited to have you. I'm super excited for this learning journey that we are about to embark on. So for administrative stuff, let me just cover a few things. So hopefully everybody saw my email that went out. If you haven't, definitely check that out. But basically, we have a syllabus here, which I will drop in the chat. So there's a link to the syllabus. And the important action item here, I would say, is so join the Google Calendar if you'd like. That'll give you alerts for all the classes, all the office hours, and so on. If you haven't filled it out, please fill out the survey for the office hours. So the office hours are going to be times that I hold in the Gather Town that you can just stop in and I'll help you with any questions related to the course. It's opportunity for one-on-one learning. So if I can pick the best times that catch the most people, that's my aim here. So your responses help me do that. There's going to be course notes posted on my GitHub. And also everything will be recorded. This will be posted on YouTube. And this is the Hacker House that we will use for office hours and other course events. Many of you were just in there for the mixer, which was a lot of fun. What else? So here's our schedule. We have 1, 2, 3, 4, 5 classes, then a 1-week break, and then another 4 classes. All you have to do is get all your homeworks in by July 28th, or 8 out of 9 homeworks, I should say, because you get 1 free drop. Get those in by this due date and you'll be a finisher. However, if you do them on time within a week, 8 days of the class, then I will get you feedback and that will surely help you learning. I'll give you comments and suggestions on the homeworks that you sent in. Yeah, so please get a planet and join the new Hooniverse. This is a friendly place where you can ask questions on the homework, on Hoon, on Urbit in general. We'll also use this for announcements. I'll send emails to you guys before and after the course, before to remind you with the Zoom link and after to come out with the notes and come out with the recording. And yeah, so I'm your instructor, Jack Tamla Modnice. Always feel free to get in touch with me. I'm very happy to help with any questions. Just DM me here on Urbit or send me an email. I currently work for the Urbit Foundation on developer relations. And before I was a computer science PhD student before dropping out and joining to fight the good fight for Urbit. So yeah, I think that's all the information that's super relevant here. And you can always read this, but I did want to take a bit of time to draw your attention to this, make sure we covered all the important points. But all right, so let's get into the meat of the course. And with this course, we're not just going to start with Urbit, we're going to go very far back. We're going to go all the way to the origins of what exactly is computing. So what is computing? I'd say that computing goes all the way back to humanity's search for truth and knowledge. We, with our large brains and evolved sensibilities, we want to understand the world around us. We want to know what is true. We want to really understand things, right? And you can even say that this ability that we have is what distinguishes us from the other life forms on Earth. What exactly is how do you represent truth? What exactly is a true statement? I can say that suppose that the city of Madrid is in Spain. If we take that to be true, then it must be true that if I live in Madrid, then I live in Spain, right? That makes sense to everybody. However, we do know that Madrid and Spain are real places, right? Most of us should know that. We can make this example a bit more instructive with another example. Now, here are some made-up locations. Suppose, take it as true that the city of Wazumba is in the country of Bajistan. Then it must be true that if I live in Wazumba, then I live in Bajistan. If you assume that this statement is true, then it has to be true that this statement is true, just based on the structure of the argument here, right? So as a logical thinker, as somebody, as when we're putting our computing hats on to understand this, what doesn't matter exactly is necessarily the truth of the existence of Wazumba or Bajistan, but the relationship, the fact that if this is true, then this is true, the relationship between these two statements. So I told you guys that we're going far back. Aristotle was one of the first thinkers to try and formulate knowledge in this way. So he made statements like, if all men are mortal, and if all Greeks are men, then all Greeks are mortal, right? Just even not considering the content, just like the logical structure of this, just is an unambiguously true statement, right? Greeks are a subset, a part of men, and men have the property of being mortal. So therefore, Greeks also have the property of being mortal. GPT-4 says the picture of Wazumba is actually in Istanbul, Turkey. Well, just imagine that it's a fake city. Okay. All right. So the problem is that the ordinary language that we use is slippery. Most of the speech we use in everyday life to try and describe things doesn't exactly fit into these very clear logical relationships. So, for example, if I say the word chair, everybody here knows what a chair is, right? But can somebody give me a clear definition, an unambiguously true definition for what a chair is? Well, some Twitter people were arguing about this. So this user says a chair is a separate seat for one person, typically with a back and four legs. Seat, a thing made or used for sitting on, and most definitely not circular. Okay, that kind of makes sense. So I guess this horse is a chair. So that's kind of the problem with language as we use it, right? It's not always 100% clear. A famous story says that Plato used to refer to a man as a featherless biped, and one day the philosopher Diogenes brought in a plucked chicken and said, "Behold, a man." So with that in mind, is there something that we can start with as a solid, clear foundation to represent what exactly is the basis of knowledge? Well, I'd say that the simplest possible thing you can do is express a difference, a yes or no, right? It's true that I have black hair, or is it false? It's true that I ate an apple today, or is it false? Yes or no, night and day, hot and cold, so on and so forth, right? This is like a really philosophically fundamental thing. You go to the Bible, and the first thing that God does in the Bible is create light out of the darkness. From nothingness, he makes the distinction of light and dark, right? And in Taoism, there is the two primordial forces of yin and yang, masculine and feminine. And this gives us hexagrams, which represent all the possible permutations of the world, right? So my point is that in all of these philosophical systems, you're going to find this distinction of like the most basic thing is just like a yes or no, right? This or that. So that brings us to the bit. A bit is a singular value which can be either 0 or 1, a simple binary choice, just like we just discussed. And this bit is a basis that we can use to represent many, many things. So what can we do with something that can either be a 0 or 1? Well, one of the first things we can do is represent other numbers, bigger numbers, other than just 0 and 1. So how might we build representations of numbers from zeros and ones? Here's one possible way we could do it. So this is an encoding of numbers by squares, which are just, let's say the white is a 0 and the black is a 1. So how do we encode the number 3 using this encoding? Well, that would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, so on and so forth, right? This is a particularly good way to encode numbers using zeros and ones. Probably not, right? Probably this is a pretty inefficient way. However, it's unambiguous. You can definitely clearly tell which arrangement of zeros and ones corresponds to a 3. So this is valid. It's not the most space-saving way, but it is definitely a valid way to encode the numbers 0 through 9 in a sequence of zeros and ones, just zeros and ones. Okay, so the usual way, probably many of you have seen this, but it's okay if you haven't. The usual way that we encode numbers with zeros and ones is called binary representation. Now, how does binary representation work? So it's pretty similar to decimal notation, tens notation that we're all familiar with. So the rightmost entry, this entry, represents the ones place. If there's a 0 here, you don't have a 1. If there's a 1 here, you have a 1. This represents the twos place. There's a 0 here, you don't have a 2, and if you have a 1, then you have a 2. There's a 0 here, then you don't have a 4, and if there's a 1 here, then you have a 4. And then so on and so forth, and then you just add up all of those to get, for example, this number is, you have 164, and then 1 4, and then 1 2. So 64 plus 4 plus 2 is 70. So this is the binary encoding of the number 70. All right. So based on that interpretation, I have this sequence of bits: 0 1 1 0 1 0 0 0 0 1 1 0 0 1 0 1 0 0 1 1. If I decode that using those rules that I just learned, then maybe this represents the number 427,603. That's just using this system, right? And maybe that's the case. However, I can also use a different rule. You can interpret this sequence of bits in a different way. There's not necessarily one fixed way to interpret the information. So if I interpret the sequence 0 1 1 0 1 as the letter M, the sequence 0 0 0 0 1 as the letter A, and so on and so forth, then maybe under this decoding rule, this represents the word Mars. And if I change the decoding rule, if I change this to mean the letter C, it represents the word cars. So the important lesson here is what matters just as much as the data itself are the rules that we apply to interpret the data, to how we decode it into meaning in our minds. So we can interpret the sequence of bits in infinitely many ways. It can be a number, it can be a word, it can be some data structure on the computer, it could be an image that's displayed on the screen. It all depends on the rules that you apply to the data to make it into something meaningful. So as an analogy here, a DNA molecule isn't a person just by itself. It's not until you have all the proteins and RNA and all the machinery to translate that DNA into a being, then it becomes a being, but a molecule is not a person, right? So all the data that makes up any computer you use, you can interpret it as just a really big number. Like your Urbit chip can be thought of as a really big number because it's a really long sequence of zeros and ones on the chip. However, what makes it into a computer that you can use that does something, that shows something for you, is the decoding rules that you're applying to that information to turn it into something meaningful for you. All right, so I'll take a pause there, just see if people have any questions. Okay. If there's no questions, we just covered zeros and ones, how data is stored on a computer, and how that data might be interpreted to become different things to the user, right? To the user of the computer. Okay, so
Hey, I think I do have a question actually. Sorry.
yeah,
Just really quickly, and we don't have to dive really deeply into this, but for me to understand things, I have to have like a physical understanding of them. And so I'm just trying to understand how we get from zeros and ones as abstract to like something on a chip, like on silicon.
Yeah, so that's a good question. So in the silicon, this gets into like hardware, but how they store the zeros and ones is they have transistors, basically like little gates, little things that can store patterns. And if
Okay.
it's if the like electrical pattern is this way, then I read that as a zero. And if it's this way, and then I read that as one. And there's even like fuzziness there because this you're talking about like a physical thing that is a pattern of electricity. So you're also applying a rule really to this piece of matter to like read it as zeros and ones, but in the end, it's just like it's a piece of matter, right? So again, that's like because sometimes like data can get corrupted, and then that's a situation in which you can't even tell if
But also like the rules of the silicon also affect what's possible with the computer, right?
Mm-hmm. Absolutely, yes.
Okay,
Mhm.
cool. Thank you.
Yep, of course. All right. So we got an idea of how information might be stored on a computer. However, a computer isn't a static piece of information. It changes and manipulates that information according to instructions to produce results, right? So a computer is something that operates according to strict, clearly defined instructions. So we can ask ambiguous things of our friends like, please give me a glass of water, and they can understand and carry that out, right? However, when we're programming computers, we can't speak to computers that way. We need to be very precise about the instructions. How do we explain this? How do we understand this language that computers need to be spoken with? So this gets us into the study of what are called formal systems. So formal system is a construct, an abstract construct, which consists of three parts, okay? So first part is the axioms. Axioms are the starting point of your formal system. They're things that you assume to be true. You don't have to justify them. They're things that are given to you. If you like to think of things visually, like imagine you're playing a game and your character gets dropped in at a certain spot on the map and they have a certain set of items. That's just like the beginning of the game. You assume that that's not something you did any action to get. That's just starting point, right? So axioms are the starting points of the formal system. Next are inference rules. So inference rules are things that you can do repeatedly, starting from the axioms to get to new places, to build new things that are true, things that exist in the system. So if you're like, you maybe imagine like Legos, it's like the ways that you can put things together to make new structures, right? And then finally, theorems are anything you can get to starting from the axioms and repeatedly applying inference rules. Okay, so it's really it's a very simple construct. You got starting points, you got rules to move through the system from the starting point, and then you have all the states that you can possibly reach that by following these rules. All right. So why is it important to study systems like this? Well, suppose that you say that the axioms correspond to the starting points of your computer, and the inference rules describe all the possible actions that you can do on the computer. Then the set of theorems, the set of places you can reach, describes the set of states that the computer can reach. This gives us correspondences, such as if a formal system has a theorem, has a place it can reach with a certain property, that's like saying this computer can reach a state with a certain property. If a formal system, if you can prove that a formal system has no theorem with a certain property, that's like saying this computer cannot reach a certain state. And if you can prove something like all theorems of this system have a certain property, that's like saying all states of this computer have a certain property. And this lets you prove things like my computer can do this, or my computer cannot crash under these circumstances. So formal systems are really powerful tools for reasoning and modeling about computers. So, and more generally, returning to humanity's search for truth and knowledge, if you believe that your formal system accurately corresponds to some aspect, some part of the world, you can make correspondences like, if I proved my formal system has a theorem with this property, then that's like saying I prove something is true about the world. Or if you prove that the formal system has no theorem with a certain property, that's like saying this property is false about the world. So let's make this a little more concrete. Okay, let's look at an example of a simple example of a formal system. Okay. And let me know if you have any questions. So we have one axiom in this formal system. It is the letters mi. It's mi. And now here x and y are variables. So x and y stand for anything, but x always stands for the same thing. Y always stands for the same thing. Like y, if you see a y and a y, those are the same anything. That makes sense. Okay. So this is your axiom. You start from the letters mi. The first rule says, if I have a string with the last letter I, the same string with u added to the end is a valid theorem. The second rule says, if I have a string that starts with m, I can double the substring after m to produce a valid theorem. And finally, the third rule says, if I have a string with 3 i's consecutively as a substring, I can replace those 3 i's with a u, and that's a valid theorem. Okay, so can somebody tell me a valid theorem in this formal system?
MIU?
Yes, and how did you get MIU?
I took the rules and I composed them together, and I saw you can put an M in front of things, and you can put an I after things, and you can put U's after I's. and I
Well,
applied all
yes,
those rules.
yes. So can you tell me? So every state of the system must start from the axiom. So can you tell me, starting from the axiom, what rules you applied to get your theorem of MI?
Okay, that makes it a bit easier. So I started with the axiom MI, and
Mm-hmm.
I applied rule 1 to get MIU.
Awesome. Great. MIU is a theorem in this system. Very good. Can somebody tell me another theorem in this system?
MIU-IU.
MIUIU. Okay, so can you tell me, starting from the axiom, the rules that you applied to get MIUIU?
Well, so we applied rule 1, according
Okay,
to what that guy just said, to get MIU, and
okay.
then you apply rule 2, where IU is X. So
Mm-hmm.
you have two X's in a row. So you
Mm-hmm.
have IU.
Very nice. Yes. So MI, you apply rule 1 to get MIU. MIU, you apply rule 2 to get MIUIU. Very nice. Okay, good theorems, guys. Um, so
Is MX MX,
sorry.
does that equal? Yeah, I'm trying to think through it because originally all like my first answer to your question was that string equals theorem. Because trying to understand what you were trying to say, like you would say string or you would say theorem, but I would be reading
Yeah,
string. So
yeah,
I
I
was
get,
getting kind of confused.
yeah. I'm mixing up the terms a little here. So the every state of the system is like a string of characters, right? Um, but like in like if I use the language of a formal system, um, like a string that I can reach by applying the rules is a theorem in the system.
Okay.
Yeah.
I'm not understanding how to produce an answer to the question now. Like
How,
the previous examples seem to make a lot of sense,
Mhm.
but I'm still confused what like the structure of the answer should be.
Yeah, so somebody said MIU is a theorem. That is
Okay.
correct. Um, your answer there would be, I start with my axiom MI. Then I apply rule 1 to turn MI into MIU. And then MIU is the theorem that you've proved in the system.
Got it. Thank you.
Yep. Uh, in rule 3, since any characters TIIIM equals TUM, yes, but you cannot reach TIIM in the system because there's no way to apply the rules to get to a state with T. But if you could, then yes, you could use rule 3 to make that transformation. Yes.
So is MXX MXS X a theorem?
Sorry?
Like would MXX MXX be a theorem within the system?
Uh, no. So the X is standing for a variable here. So you can't, there's no way
Okay.
you can't start from here and apply these rules to get something with X's in it.
Okay.
Maybe this notation could definitely be clearer, but yeah, like everything in this system, there's only M and I's and U's because you only start with an M and I, and the rules only let you manipulate M's and I's and U's. If that makes sense.
So how would you get MIM?
You can't get MIM either.
You can't get MIM.
Mhm.
But what if I wanted to get MIM? I would need to make new rules.
Yeah,
Okay.
You'd have to use a different system. Mhm.
Gotcha.
Yeah, good question. Okay, so we went over this, but here's an example derivation. So you start from MI, you use rule 1, sorry, rule 2 to double this to get MII. You use rule 2 again to double this to get M-I-I-I-I. Rule 3 says if you end in I, Rule 1 says if you end in I, you can put a U. Rule 3 says you can make 3 I's into a U, and so on and so forth. Okay, so hopefully you guys get the idea there. I won't belabor it too much. Yes, thank you, Isaac, for recognizing the reference. Okay, so let's move on to another example of a formal system. So here, here I'm using the x as a variable again. Okay, so x stands for something, and in particular, x stands for a string consisting of only dashes. Okay, so if x is 1 dash, this would be dash p dash q dash dash. If x is 2 dashes, then this is dash dash p dash q dash dash dash. All right, so this system, it doesn't have one axiom like the MI system. This actually has infinitely many axioms, and that's generally okay. There's infinitely many possible starting points of this system, and that's okay as long as you specify. So all the axioms are like dash p dash q dash dash, so on and so forth, because this x can stand for any number of dashes, right? Let me know if that makes sense. Okay. So what are the rules of the system? So the rule is if you have something P, something Q, and something, and I use the star here to denote that these aren't necessarily the same. This is just something is here. You can always make a new theorem by adding another dash after the P and adding another dash after the Q. Okay. So here's an example of a derivation in this theorem. So an axiom is dash P dash Q dash dash. Then I use the rule to add another dash here, and I add another dash here. Excuse me. And this is a derivation in and of itself. Here's another axiom, 4 dashes, P, 1 dash, Q, 5 dashes. I use a rule to add another dash here, add another dash here, add another dash here, add another dash here, and so on and so forth. Okay, so this seems kind of like a boring system, but there's actually something interesting about this system. Can anyone tell what's the interesting property about all the theorems in the system?
They represent addition, right?
Yes, very, very nice. So in particular, can you expand on that, Clay?
As in, like, all the theorems in the system can be interpreted as A plus B equals C.
Yes, because the number of dashes here on the left plus the number of dashes here in the middle always equals the number of dashes here on the right. And that is true for every possible theorem in the system. So in particular, for every true mathematical statement that looks like x plus y equals z, there's a corresponding theorem in this system of p's and q's and dashes. So in a way, we modeled a simple computer which can represent all the possible true facts about adding two positive whole numbers. So if any like addition of two numbers you could think of is in fact a theorem in the system, you know, like 2,500,000 whatever plus 1,000, like that's a theorem in the system, even if it would just be a really, really long theorem. So this is how like even something simple like this can like have meaning arise out of it, right? You can like interpret the symbols that are being pushed around by your formal system into something that has meaning for you, right? However, we do have to be careful because if you wanted to do dash p dash q dash dash dash, maybe that looks like 1 + 1 + 1 = 3, but there's no theorem in this system which has two p's. So you can't go overboard by saying that this represents additions. Like you can't make the meaning inject more into this formal system than it actually can represent, if that makes sense. So let's look at one last formal system, and this is going to lead into what's going on with Urbit and Hoon and Knock. All right. So the theorems, the states of the system look like these binary trees. They're either numbers or they're these binary trees which have an arithmetic operation at the top, and in its branches are other either numbers or binary trees. Okay, so these are all the starting points of the system, and here are some examples. Like the number 5, the starting point. The number 167 is a starting point. This tree is a starting point. This tree is a starting point. Okay, and what are the rules that we can apply to transform these into other states? The first rule says if A and B are numbers, then add AB transforms to the number that you get by adding A and B. If A and B, these two subtrees, are numbers, you transform this tree into the number that you get by subtracting B from A, right? And so on and so forth for the multiplication operation and the division operation, okay? So basically, if you have a tree and under it there's numbers, you can perform that operation, collapse it into a single number, right? So we take this axiom right here. It's add at the top. On the right is a 5. On the left is a tree. That tree has a mole and 2, 3. We're going to say rule 3 says I can reduce this mole tree into the number that I get from multiplying A times B. Multiply 2 times 3, I get 6. Reduce this. Now I have this tree. Now rule 1 says that I can reduce an add tree that looks like this by adding the two numbers. And then you get the number 11. Right? Does that make sense to everybody? Okay. So this is a very simple system which models like the basic arithmetic that we're all familiar with. So let's zoom out a bit and go back to our topic of computers and information, right? So what exactly is a computer? So you sit down at a computer and there's a lot of possible things you can do, right? You can click this button, you can click that button. You can put some value in a form, you can press enter, you can close a window, you can turn the computer off, you can turn it on. You know, a computer its job is to produce a valid output given any input, any possible interaction that you do to it, right? It's waiting for an input, and then it's going to do something based on that. So you might think of a computer as a process which maps inputs to outputs. So how might we model this inside of a formal system? So how about something like this? So this looks like this tree that we just saw. But here we have this x, and this x is not a number. It's a symbol representing any possible number. And according to the rules of our system, we can't reduce this because x is a number. We don't know what number that is. So this is waiting. This is like kind of a frozen computation that's waiting for something to be here. And once you put something in there, then you can reduce it according to the rules. So, for example, we have this tree with this x sitting right here. We perform the operation to substitute 10 for x. Then we apply rule 3, which says we can reduce this subtree into 30. Then we apply rule 1, which says we can reduce this add subtree by adding 30 and 5 to get 35. So we substituted, reduce, you get 35. You could also substitute a whole expression into another expression. Okay, so here we're going to say x is the tree sub z1. Okay, so x is this. And we start with this, mole yy. Then we're going to say, let's take x and put it into y, this variable right here. Let's put x into y. That gives us this. Then the only variables in this tree are z. After we substitute z equals 9, then we get a tree with only numbers in it. Okay. And now after we get this this with the substitution, then we can apply our rules. So sub 9,1 reduces to 8, sub 9,1 reduces to 8, mole 8,8 reduces to 64. Okay, so we perform 2 substitutions. We sub this tree for y here, then we sub a number for z, and then we applied the rules to reduce this to a final definite result. You could also done what we just did here in a different order. So we're still having x is this tree sub z1. What you could have done in a different order was first you substitute z equals 9 into x first. That gets you this, which you can then reduce sub 9,1. You can reduce that to 8. And 8, this means that 8 is the value that you get when substituting 9 into x. Then you can substitute that into this original expression to get mole 8,8, and that is 64. Okay. So these are 2 different ways of doing the same thing. That makes sense to everybody. Lily says, so it always starts from the bottom of the tree. Yes, we start from the bottom of the tree because if you have something like this, you can't reduce this add. Why? Because the rule says both children of the add have to be a number before you can reduce it. This rule 1 says if A and B are numbers, then you can collapse this. But this is not a number, so that's why you have to start from the bottom. You have to make, but this mole has both numbers here, so then you can collapse this according to the rule. Yep, good question. Okay. Okay, so the big payoff. Why did we do all of this? It turns out that I've just introduced you to the basic ideas behind functional programming. Functional programming is a way to think about programming where everything is a function, a pipe from inputs to outputs. Okay. So here are the arithmetic diagrams we just covered, written in a functional language pseudocode. Okay. So our first function, fun1, takes a z and returns z minus 1. Our second function, fun2, takes a y and returns y times y. If we compose these functions, this means we're going to put some input into fun1. We're going to get that output, and then we're going to give that as input to fun2. So we're putting something into fun1. We're seeing what comes out. We're taking what comes out of that, putting it into fun2, and then we get the result. We kind of glued these together, right? So now we're saying fun2 of fun1 of 9 is 64. So fun1 is like our x here, and fun2 is like our this guy right here, well, y1. That makes sense, everybody? Okay. So some of you might be familiar with programming in an imperative language like C or Python. In this paradigm, the computer has a certain state, and then you give it various commands, say, do this to change the state, and then do this, like a sequential steps, sequential commands, right? So in an imperative language, you might say, take your input Z, set Z to Z minus 1. So set 9 to 8, set 8 to 8 times 8, output 64. We have to move away from this kind of thinking. In a functional language, everything is a function, a map, a pipeline from inputs to outputs. So if you want to combine operations, you glue them together. So again, we're representing that we have our input of 9. We pass it through this function. f1 of z equals z minus 1. You get 8. You pass it into this function. f2 of y equals y times y, and you get 64 as your output. Any questions? Okay. So in general, so a functional program in general consists of two things: the data input and the function, the sequence of operations that you're going to do on it, right? Let's look at a simple example of functional program on a simple data structure called a binary tree, and it'll become very apparent in the next lesson why these structures are important. So a binary tree is a tree structure, or each node either contains a number and no children, or it splits into 2 branches, each of which can contain numbers or continue splitting. So this is a simple data structure that we're going to work with. Now let's study some functions on these data structures. Okay. So the function left subtree is going to take a tree that looks like this. This is the input. Get you the left subtree. So everybody sees why 531 is the left subtree of this, right? Great. All right. So right subtree. Same idea. We have this tree as the input, and we are grabbing the right subtree of it. In this case, it's just the number 2. And finally, we have another function here, which is increment. So if this is a number, then you just increment the number. If a function is invalid, we're going to get a crash. So if you give 5 to this, you're going to crash because there's no subtree here. If you try to increment something that's not just a number, you'll also crash. Okay. So with these data inputs and these functions, we can compose together more complex things. Can anyone tell me what the output of this function will be on this input?
3.
Yes, very good. Because the right subtree of this is number 2. Incrementing the number 2 gets you the number 3. Very nice. Okay. Can anyone tell me what will happen on this input and this function?
Crash,
Yes. And why will it crash?
because the left subtree is not a number.
Yep.
It's run tight.
Yep. So left subtree of this, 17.8, trying to increment that will give you a crash. All right. So pretty straightforward so far, right? In the next lesson, we start to understand the basics of Urbit. It'll become very clear why these are important. So going back to our pseudocode functions, functions can call other functions in their definitions. So this is what we had before, right? This first function takes something, decrements it. The second function takes something and multiplies it by itself. We could also rewrite these if you want to compose them this way. So function 1 takes a number, reduces it by 1. Function 2 takes a number, calls function 1 on it, and then calls function 1 on it, and then multiplies those two. So this, we kind of rolled our composition in here. So instead of having to do this, pipe them together, all you have to do now is call function 2 on the number 9. That's going to take the number 9 and give you 8 times 8 is 64. But even more interestingly than this, functions can even call themselves in their own definitions. And this is a very important concept called recursion. So let's consider this program right here. Okay, so let's figure out what this program does. We give it an input 0. It's going to say, if n is 0, which is true, return n. Then it's going to return the number 0, right? So you give it a 0, it'll give you back a 0. Okay, if we give this the number 1, what's going to happen? If 1 is 0, 1 is not 0, we're going to go here, then return the result of calling itself on 1 minus 1. Now we just reasoned that function of 0 is 0. So that means when you give this a 1, it's going to take this branch, calculate function of 0, which is 0, and return 0. So function of 1 is also 0. Now, if we throw in a 2, what's it going to do? It's going to go here. Is 2 equal 0? No. It'll take this branch, return function of 2 minus 1. That's function of 1. Now, we just reasoned that function of 1 is the same as function of 0, which is 0. So that means if we throw in a 2 here, we'll also get back to 0. So can anyone tell me what this does for any positive whole number that you give it? Yes.
Ultimately returns 0.
Yep, it returns 0 for every positive whole number. But there's also potential. So this is very simple, straightforward example of recursion, right? But there's also potential dangers with recursion. Now, what does this function give us for an input of 0? We throw 0 in here, 0 equals 0, yes, return 0, that's fine. However, if we throw a 1 in here, function of 1 is 1 equals 0? No, go here. So calculate function of 1 plus 1 equals 2. What is function of 2? Is 2 equals 0? No, go here. So calculate function of 2 plus 1, function of 3. What is function of 3? So what's going to happen here is if you throw 1 here, the computer will never be able to figure out the final thing it should give you. It's just going to keep looping and looping infinitely because there won't be a condition that tells it to say, okay, here's the output, we're done. Like, here's what you get.
Hopefully eventually you run out of memory.
Yep. Mm-hmm. Okay. So the important thing here, these functions are referring to themselves, and that's completely okay in functional programming. Now, the other thing is, in programming, it's often important to consider how many operations it takes to compute a result. So this is our first example of a recursive function. How many operations, how many calls to the function does it take to compute an input of 0? How many times does function need to call itself to return the result on an input of 0? Just once, yes, because if I give it a 0, it's going to say if 0 equals 0, yes, return 0, you're done, no more looping, right? If I give it a 1, how many times does the function need to be called to give a result?
Two times.
Yes, very good. And I see Hassan has put a correct answer in the chat, which is on an input of n, this function will need to be called n plus 1 times to return a result. And always just return 0, but we're just talking about how long it's going to take, right? And in computer science, this is what we call O of n time. We don't need to go too deep into this, but basically it's saying the amount of time it takes is roughly linear in proportion to the input that you give it. So if you give it an input of 10, it's going to take similar to 10 cycles or like something that scales with that number to return a result. Okay, so now I have a new function for you guys to consider. It's a little trickier. First, what does this function do? Well, let's reason through it. If you give it a 0, if n equals 0, return 0. Okay, same as before. If we give it a 1, here, it's going to return function of 1 minus 1, which is function of 0, which is 0, plus function of 1 minus 1, which is function of 0, which is 0. So if I give this a 1, it's going to give me back a 0, just as before. If I give it a 2, it's going to say, is 2 equals 0? No. So return function of 2 minus 1 plus function of 2 minus 1. That's function of 1 plus function of 1. But we just reasoned that function of 1 is 0. So if you give this a 2, it's going to return 0 plus 0 equals 0. So this thing is really going to give the same exact outputs as this other function we're just looking at. However, how many cycles does this take to return a result? This is kind of different here. If I give this an input of 2, it's gonna call function of 1 twice. Function of 1 need to call function of 0 twice. So basically, the number of calls that we're going to take here is going to grow exponentially. So it's very different from this thing here. Even though it returned the same result, it's always just going to return 0. This is going to if it takes n, if you give it an input of n, it's going to take an input. It's going to take a time that's roughly 2 to the n calls to the function. Okay, so hopefully that made sense. This puts a wrap on our short introduction to the fundamentals of computer science. Now, hopefully you guys have a couple more minutes. We're just going to quickly go over what you'll need to begin developing software. Okay. So to write software, you simply need the ability to write text and save it as a file. Technically, you can just write in like a simple text editor, but that doesn't have very many tools to help you write code. Most people use what software called an IDE, or an integrated development environment. The one that I like to use is called VS Code, and I'll show you right here. This is VS Code or VS Codium. It's a very popular text editor for writing code. So maybe if you're a software developer, you know already what you like, then simply use what you're used to. If you're new, I suggest downloading either VS Code or VS Codium, which is the open source version. We'll have more information on this in the homework and the notes. Next, you should be comfortable using Git, which is a tool for programmers to upload their projects, create backups, and collaborate with other programmers. If you haven't used it before, we'll just have a very short assignment for you to get comfortable with the basics of using GitHub. And finally, the last skill that you should start getting comfortable with is using the terminal. So probably you've seen this thing. You may associate it with elite hackers, but it's not terribly complicated. So there's just a text-based interface that lets you access your computer and give it commands. And once you, for this class, you'll just need to get a few basic commands that you'll be able to learn, like change directory, and list what you see there, and so on and so forth. But yeah, in summary, to get started as a software developer, you should get an IDE, learn how to write code in here, learn how to use Git, and learn how to use the terminal. We'll have bits in the homework that'll help you get started on these things if you have any questions. All right. Well, thank you everybody for being here for this first class. Now I'll open the floor to questions. Can Hoon do dependent types? Good question. Can you elaborate exactly what you mean by dependent types?